I will now be showing you how I created the Poisseuille flow and a two-dimensional laminar incompressible flow. Um, and here we have our two-dimensional shape, our length, our height. We made this a solid surface. First, we sketched our model with our sketching tool. We used lines, connected them all to create our shape. Next, we used our dimensions. We went here, we dragged down our length to determine our length. We converted the units to millimeters because that's what our pipe is calculated in. The same thing can be done with our height. I've done this before the video because it takes too long to do into the video, so I'm just showing you the process. But once that is completed, we went to our concept. We went to surfaces from sketches. We clicked that. We were able to essentially draw a box around the selected figure and put a face on that figure, so it has a solid surface. Following this, the next portion is to do the meshing. And meshing is done by adding small divisions multiple times on each part of the figure to have a more redefined figure when you complete the simulation. This is done by, if we go down to our mesh here, you start off by initializing the mesh with the automatic method. You then go down to edge sizing, which is where you basically choose your right and your left side edges, your inlet and your outlet. And you basically set a number of divisions to do for that. So here I chose 250 divisions between the left and right side. For our edge sizing 2, this was between the top and the bottom. I used 400 divisions because more divisions on that because the velocity profile is going to be running in the vertical direction. The final step was to do the face meshing, which is essentially what kind of brought everything together and had this very clean looking mesh. And then the last step, I guess, would be to name your selections. So we have our inlet, our outlet, our top, and our bottom. And that's just going to help us when we move to the next step. Let's see, how do I share the screen? Next step would be to do our solver, which is basically setting our conditions for the model to run smoothly. This is a laminar flow, meaning that the Reynolds number is below 2100. For our materials, we are going to be using air. If we click here, you can see our density is 1.225 kilograms per meters cubed, and our viscosity is 1 times 10 to the negative 4. Closing that out. Our boundary conditions, our inlet, we're going to have a velocity of 10 meters per second. That'll be our velocity inlet. Our top and bottom plates are considered walls and are stationary in this video. And the outlet is the pressure outlet, and we're going to leave that as 0 velocity for now. I'll bring that up really quickly so you can see. Perfect. Closing that out, we can next go to our reference values, and we're computing from the inlet. That's where our values are going to be beginning. As you can see, the density is still 1.225. Temperature is going to be 288.16 Kelvin. We're going to leave that alone. Velocity and viscosity are going to be based on the values we input in our in the previous area over here in the materials section. So we're going to close this out, and we're going to go to, after this is complete and all these values are set up, you can go to the initialization portion. You click initialize, and that prepares it for the calculations portion. Once the initialization complete, you click the run calculation down here. You want to make sure there's 500 iterations, making sure you have enough iterations to converge on your answer, because if you don't have enough iterations, it's just going to not be a pinpoint answer. It's not going to be close enough for you to use in your calculations, and your simulation will be messed up. You click calculate, it gives you the graph with the iterations and the residual, showing you that you indeed converge to an answer. Once this is completed, you can actually move on to the next step, which is going to be calculating, or not calculating, but displaying, what would this be? The contour of the velocity profile. So here, I'm going to actually just click contour, and we're going to call this velocity profile. Okay. We can go down here. Let's see, we're going to put that back to all domains. Our variable is going to be velocity u. It's going to be global. Number of contours, we're going to choose, we'll do 100. Actually, we'll do 200 to have a more refined contour. And then we can apply that. And it seems, one moment here, let me switch. For some reason, this is buggy here. Velocity u, global velocity profile. It should be over this. Let me adjust this really quick. Apply. Let me try with 100 contours and see if that works. Contour is on. Labels, render, view, geometry. Oh, symmetry 1, that was the issue. Okay. We apply. And as you can see, we have our contour of the pipe with a diameter of 10 millimeters and a length of 500 millimeters. Going down and scrolling in a little bit, giving some explanation, you can see the boundary layer develop over the course of the pipe. As you move down the length of the pipe, you can see the velocity kind of stays pretty constant in the middle, and the velocity or the boundary layer on the edges of the pipe kind of evens out. And it starts kind of, as you can see, the boundary layer kind of increases as you move along the pipe. And that's just due to the viscosity of the air. So next, I'm just going to very quickly plot a velocity profile of the halfway point on the pipe and the final point of the pipe to see how they change. For that, I'm going to first take off my contour. Second, I'm going to insert lines. This is going to be the 250 millimeter mark. Okay, and we're going to set that our x point to be 0.250 with our y being 0, and the next point will be 0.250, and our y will be 0.01, indicating the full length of the diameter. We're going to apply that, and you should see we get our line. Lastly, we have to do the one other line here. This is going to be at the 500 millimeter mark. Okay, we're going to set that to 0.5 meters, 0.5 meters, and again, our diameter of the pipe, which is 0.01 meters. We're going to apply that, and as you can see, a little yellow line comes up here. Once we have that set up, we can actually make a chart here. So we're going to click the chart button. We'll just call this velocity profile again. Okay, velocity profile already exists. So we're going to call this velocity profile and P flow. Okay. Here we have our chart here. I'm going to call this velocity profile again. And we're going to call this case A. Case 1. Our data series, we're going to go here. We're going to click, this is going to be at the 250 millimeter mark. And then we're going to pull that source from our 250 millimeter line we made. And we are going to, first actually, we're going to have to initialize our X and Y axis. Our X axis is going to be velocity U. Our Y axis is going to be just the Y axis, change in velocity. Now we can go back to our data series and apply this. And as you can see, we get a curve of the velocity profile at the 250 millimeter mark. Repeating this, now we go down to add another series. We're going to rename this to our 500 millimeter mark, like this. Our location is going to be on that line we created at the very end by the outlet, and we're going to apply that. As you can see here, the velocity profile is more defined at the 500 millimeter location because the length of the pipe has, or the longer the pipe is, the easier it is for the velocity profile to be fully developed, which you can see here. And that concludes the first part of this assignment.